Hi. In the last section, we talked about applications of maxima and minima. Mainly, we talked about optimization. Now, what we're going to do is talk about higher order derivatives. Specifically, we're going to talk about acceleration and concavity. Now, you might be wondering where in the heck are we going with all of this information, with all of these calculus techniques. The tools that you're learning in chapter 12 is leading you to a point where you're able to analyze the graph of a function. That's our ultimate goal for chapter 12. But in order to do that, you need to be comfortable with finding maxima and minima. You need to use the first derivative test, and you need to learn how to take higher derivatives to see what kind of information you can get from that. Now, our goal in this specific section, we want to make sure that we learn higher derivatives in their applications. For example, suppose you're driving a car and the velocity is changing. The rate at which your velocity is changing is called your acceleration. Now remember that your velocity was the derivative of your position function. So now if you're talking about the rate at which your velocity is changing, you're talking about taking the derivative of your velocity. But that will be the second derivative here. So mathematically, we find the acceleration by taking the second derivative, which is the derivative of the first derivative. So let's start out with the definition. If a function f has a derivative that is differentiable, then its second, that's an s, so let's make it better. Then its second derivative is the derivative of your function. So in other words, it's f double prime. The two ticks here means you're taking the derivative twice. Next definition, the acceleration of a moving object is the derivative of its velocity. That is, it is the second derivative of your position function. Notation for the second derivative of f, use either f double prime of x, or in Leibniz notation, you'd use the second derivative of f with respect to x. That's what that means. So again, this was Leibniz notation. And this was prime notation. Okay? Now, back to this definition quickly. Remember, we said it's the second derivative of the position function. Note that your position function was s of t. S prime of t was your velocity. S double prime of t is going to be your acceleration. Okay? So now, given the position function, s equals negative 12 plus t minus 16t squared in feet as a function of time t in seconds, we want to find the following. We want to find the acceleration as a function of t or time, and then b, we want to find its acceleration at time t equals 2. So if you want, you might want to write, instead of s, you can write s of t. It's not incorrect to write what I had, but if you want it in terms of t, you can write it that way. Now, s prime of t, as we discussed on the previous page, s prime of t is your velocity. That's v of t. Well, the derivative of negative 12 is 0. So that would be 0. The derivative of t is 1, so plus 1. The derivative of negative 16 t squared would be negative 16. Bring your 2 down, so times 2t. So that would give you minus 32t. So an aside, make sure you're comfortable with derivatives right now. I'm just writing this out because some of you might have the question, where did that come from? So the derivative of this is equal to negative 16 times 2t squared, which is negative 32t. Okay, so s double prime of t. That's going to be equal to a of t. A of t is your acceleration. That's equal to the derivative of 0. Well, that's not even there. The derivative of 1 is 0. Then the derivative of negative 32t, negative 32t, is negative 32. But we're talking about the acceleration, so that's feet per second squared. That's our answer. Now, in part B, we want to find the acceleration at time t equals 2. That means we need to find a of 2. There is no place to substitute 2 into. There is no t specifically here. So a of 2 is just going to be negative 32 feet per second squared. That's it. Okay? Now, other things that will help you in learning how to analyze a graph in the future will be the following. Okay? We need to learn the terms. A curve is what we say concave up. And we've talked about concave up and concave down before, but now we're putting the idea of the second derivative with it. So a curve is concave up if the second derivative is positive, which implies the slope of f is increasing. A curve is concave down if f double prime of x, or the second derivative, is negative, which implies the slope of f is decreasing. Note that if the second derivative is positive, that implies the slope of your original function is increasing. And you have concave up. If f double prime of x is less than 0, that implies the slope of your original function f is decreasing. Now, if you want to know what happens whenever your function changes concavity, that's called a point of inflection. A point of inflection is a point in the domain of your function, your original function, where the graph of f changes from concave up to concave down or vice versa. So if your original function changes from concave up to concave down, you have an inflection point. If it changes from concave up or concave down to concave up, you have a point of inflection. Okay, so now we have the graph of this function here, and we want to talk about concavity and we want to talk about points of inflection. So here, let's notice that we're looking at this shape. This shape is concave down, right? CD for concave down. That means our second derivative is less than 0, and we can make that better. So that means our second derivative is less than 0 here. And note that from this point on, from that point on to this point, the graph is concave up. Well, that means that our second derivative is greater than 0. Well, notice that it changed concavity at this particular point. So that would be a point of inflection. And sometimes we just say inflection point. And notice here, it changes back and we get this shape, which again is concave down, which means our second derivative is less than 0, and it changed concavity at that point. Since it changed concavity at that point, that's an inflection point or a point of inflection. Okay? So where does this actually come into play? It comes into play in these types of examples right here. The following graph shows the approximate value of the U.S. Consumer Price Index, the CPI. Okay? from September 2004 through November 2005. We have this curve, okay? The approximating curve shown on the figure is given by I of t equals negative 0.005 t cubed plus 0.12 t squared minus 0.01 t plus 190. And the close on the interval t is greater than or equal to 0 but less than or equal to 14. So that's your domain for x, 0 to 14. Okay? Where t is the time in months since the start of September 2004. Okay? Now we want to use the model. We want to use I of t to estimate the monthly inflation rate in July 2005 for t equals 10. Recall that the inflation rate is I prime of t divided by I of t. Where would you recall that from? You would have to read your book. That's in page 938 for the explanation of your recall. Okay? That's something that, if necessary, you would be given that. But now that I've given it to you, I'm expecting you to know it. Okay? So, now we want to use the model to estimate the monthly inflation rate in July 2005, which means t equals 10. So let's write down, we need to know I prime of t. Notice that the inflation rate is given by I prime of t over I of t. So that means we need to find the derivative. Take a minute, pause the video, write down the derivative so that when I write down what I'm writing down, it will make sense to you. Find the derivative of I of t. So find I prime of t. Now that you've found that, I prime of t, the inflation rate is I prime of t divided by I of t. So I prime of t is negative 0.015 t squared plus 0.24 t minus 0.01, all divided by I of t. So negative 0.005 t cubed plus 0.12 t squared minus 0.01 t plus 190. That would be your inflation rate. Now, for July 2005, that means t is equal to 10. Now we substitute in 10. So the inflation rate would be I prime of 10 divided by I of 10. You can use your calculators. What you're going to do is plug in 10 in each part where there's a t. Be careful. Put all of this in your numerator in parentheses. When you substitute in 10, put that in parentheses. Put all of your denominator in parentheses. That will make a difference on your output for your answer. Whenever you do that, you should get 0.89 divided by 196.9. And that's going to be approximately 0.00452, or in other words, 0.452%. So in other words, you would multiply this answer by 100 because you're looking for the percent, right? So that's estimating the monthly inflation rate. There you go. Now, continuing with that same example, was inflation slowing or speeding up in July 2005? Well, whenever we ask, is inflation slowing or speeding up in July 2005, that means we need to talk about the derivatives, right? We need to talk about the second derivative to figure out if it's going to be positive or negative, specifically. So we need to remember I prime of 10, which I prime of t, which we found on the previous page, was equal to negative 0.015 t plus 0.24 t minus 0.01. Okay, now we find the second derivative. What does that mean? That means we need to differentiate this function. Going back up, that should have been t squared, right? So now we want to differentiate this function here. So I double prime of t, we differentiate this, we get negative 0.030t plus 0.24, and I double prime of 10, because we want to figure out what happened in July 2005. So I double prime of 10 would be equal to negative 0.030 times 10 plus 0.24 is equal to negative 0.06. Well, what does that mean? That means since I double prime of 10, that's double prime, I double prime of 10 is negative, inflation was slowing down. Okay? And that means it was slowing down in July 2005. If we want to know when was inflation speeding up and when was inflation slowing, then that's asking us to find it in general. Okay? So when was inflation speeding up and when was inflation slowing? Then we are now needing to know what are the points of inflection. So in other words, what are your points of inflection? So your points of inflection occur when your second derivative is equal to 0. Graphically, that means you have a horizontal tangent. You have a horizontal tangent there. Okay? Now, here, you look at your second derivative. We found our second derivative up here. Let's call that smiley face. That's an interesting smiley face. So that's I double prime of t. So that's what we're going to do. We're going to use that down here. So we have negative 0.030t plus 0.24 is equal to 0, or t is equal to 0.24 divided by 0.030. That means t is equal to 8. Well, looking at our graph, so now you have to look back on the previous page. So looking at the graph, let's see. So if we look at our graph here, okay, t is equal to 8 about here. Looking at the graph, we see it's concave up. The shape of that is concave up to the left of t equals 8, and it's concave down to the right. Okay, which means there's an inflection. That means inflation was speeding up for t less than 8, but then it was slowing down for t greater than 8. Okay, so looking at the graph, let's just write that out. So looking at the graph, we can now say we see that it is concave up to the left of t equals 8 and concave down to the right. Therefore, that means inflation was speeding up for t less than 8 or before May, and slowing down for t greater than 8. In other words, after May. That's your answer. Okay, so now that we've learned about second derivatives, there is a second derivative test. So the second derivative test allows you, or gives you another tool in your belt where you can find your relative minimum and your relative maximum. Okay, a lot of people don't use this test often. It's just another test that you could know or need to know and know how to use it. Okay, so the second derivative test for relative extrema, suppose that f prime of c is equal to 0. So in other words, suppose you're looking at a critical point. Suppose c is a critical point. Suppose that f prime of c is equal to 0 and that f double prime of c exists. Determine the sign of f double prime of c. So determine whether it's positive or negative. If f double prime of c is positive, then f has a relative minimum at c. If f double prime of c is less than 0, then f has a relative maximum at c. Note, if f double prime of c equals 0, then your test gives you no information. It's inconclusive, and you would need to use the methods from section 12.1 to find your relative extrema. So in other words, you could use the first derivative test, you can test your endpoints, you can use that information. So, example 3, we want to, given f of x equals x cubed minus 3x squared minus 9x, we want to use the second derivative test to find the relative extrema. So, we first need to find, according to the definition, we need to find when f prime of c is equal to 0. We need to find that c. So, we need to find f prime of x. So, f prime of x is equal to 3x squared minus 6x minus 9. That is equal to, notice that all of it has, each term here has a 3. So we can factor that out. We get 3 times the quantity x squared minus 2x minus 3. And then you can factor that as 3 times the quantity x plus 1 times x minus 3. Pause the video and review how to factor if that seems confusing. Now, f prime of x equals 0 means that 3 times the quantity x plus 1 times x minus 3 is equal to 0. Well, that means x plus 1 is 0, or x minus 3 is 0, because you can divide both sides of this equation by 3, and that gives you this. So that means x equals negative 1, or x equals 3. Now, f double prime of x, so this is our c. Okay? So, x equals negative 1 and x equals 3 are c values. So all we've done so far is we've done that. But this says and we need to check to make sure f double prime of c exists. So that means we now need to find the second derivative. So let's find the second derivative. The second derivative for this function, I'm going to go up here, f double prime of x is equal to, now we're differentiating this function here. So differentiating that, we get 6x minus 6. Now we need to make sure that f double prime of c exists. So now we need to plug in negative 1 into this, plug in 3 into this to see what we get. So f double prime of negative 1 is equal to 6 times negative 1 minus 6, or we get negative 12. Okay, well, wait a second. If we look back at our second derivative, If we get a negative number, that means our function f has a relative maximum at c. So there is a relative maximum notice that it's a maximum, not a minimum, at -1. Now let's find f double prime of 3, because that's our other c value. Well, that's 6 times 3 minus 6. 18 minus 6 is equal to 12. Now we get a positive number. So that falls into part 1. If f double prime of c is positive, then f has a relative minimum. So there is a relative minimum at 3. Okay? And that's it. Okay? Example 4, higher derivative notation. Higher derivative notation. Before we talk about example 4, let me introduce the notation to you. If you want to find the third derivative, prime notation, f triple prime of x, or d3 of f over dx cubed, which means take the third derivative of f with respect to x. Fourth derivative, after 3 ticks, we don't write 4 ticks anymore. We just write the number. So the fourth derivative would be written this way or this way in Leibniz notation. So now for f of x equals e to the 2x, we want to find the third derivative and the fourth derivative. So let's do that. So f prime of x. F of x is equal to e to the 2x. F prime of x is equal to e to the 2x times the derivative of 2x. That's e to the 2x times 2. Written better is 2e to the 2x. Now, f double prime of x means we want to find the derivative of that. Well, that's equal to 2e to the 2x times the derivative of 2x. Well, that's 2e to the 2x times 2, or 4e to the 2x. F triple prime of x is what we get when we differentiate that. So this is 4e to the 2x. We get itself times the derivative of 2x. It's the chain rule part. So you get 4e to the 2x. By now you probably know what we're going to have, times 2. And that's 8e to the 2x. But now we want to differentiate this one. So that will give us the fourth derivative of x. And you're probably guessing correctly, you're going to end up with 16e to the 2x, but let's write it out. So you would have 8e to the 2x times the derivative of 2x, which gives you 8e to the 2x times 2, or 16e to the 2x. And that's it.